I think we can start. Yeah, good morning, everyone. I don't know if you can say morning still, but it's before noon, so let's start. And thank you for joining my session. I know Jennifer's is very interesting to happening in some room next door. Today, I will be talking to you about predicting the future and how to use Azure ML to do it, and how to actually use it in the form of a service on Azure. Who am I to talk to you about that? I used to be a programmer. I switched the field, and now I am a data solution architect. I have a background in machine learning. I was doing my PhD, my master's degree in machine learning. Currently, I am employed by Microsoft, and I'm talking to the clients about their data solutions, about databases, how to use predictive analytics on them. Today's agenda will be surrounded mostly on machine learning topic. So I'll give you a brief introduction on what I understand machine learning is, because wherever you go in the internet nowadays, there are different definitions. You probably have your own. I'm not saying mine is correct. I'm just saying it's mine. So I will tell you what I think machine learning is. And then I will show you the capabilities of the tool, which is Azure Machine Learning Portal. I will show you how to create an experiment, so it will be heavily demo-driven part. And then how to productionize your solution once you have your model built. Then I will talk to you about how you can collaborate your solutions or use the solutions produced by other people and how to collaborate with the community. So let's start. What is machine learning? What do you think? We have quite a few people. We hear it in all those sci-fi movies and books, and basically it's a big hype at the moment. What do you think machine learning is? Anyone? Yes?
The definition I heard earlier in the week was it's a piece of software which the performance of which can improve without actually changing the code.
So one of the definitions is a piece of software that improves, basically learns, right? Yes, that's a very, very valid definition. Anyone else? Yes?
Making judgments based on data sets.
Making judgments based on data sets. This is actually how you use when your machine learns, when your algorithm learns, then you're making judgments or predictions for the future data based on the historical data. Yes, very, very well. No one said anything about artificial intelligence or robots. Deliberately put it there. You probably know a lot on the topic. So artificial intelligence is something that is broader. And machine learning is one of the fields inside of artificial intelligence. And we had a panel yesterday on machine learning, and I think we covered it quite a bit on how different words can change, maybe not the meaning, but the perception of how people feel about the field. Anyone else wants to share what they think machine learning is? Yes? Optimization. Very good. I was actually waiting for that answer, which I almost never get. So like back in the days, like 10 years ago, when you were doing, for example, data mining, or what was said artificial intelligence was back then, it was solving optimization problems. So you had a function and you were trying to maximize it or minimize it in the most efficient way, because standard maths or standard modeling didn't give you that answer quickly. So computation was very expensive. I will walk you through my definition, but before we go that, I would like to stress it that we are living in very exciting times. And I read this quote, well, literally like 10 years ago for the first time, probably late to the party. And then I started reading Harry Potter, and then I started watching movies with Harry Potter. And I had this feeling that those guys, especially Hermione, are like very good hackers. They really know all the spells, which is basically commands or the syntax all the programming languages, and they really know how to use it. And even though it was about magic, right, for me it was knowledge. It was those people knowing what they're doing. There was nothing magical about them, especially when you think of Hermione. I'm sorry for not Harry Potter fans, because they were learning how to use it, they were practicing how to use it. And then, if it was advanced enough, it appears as magic. And today, if we see all the applications of artificial intelligence, cognitive services, and machine learning, it really sometimes resembles it. This is the example I encountered in several books and articles, and it's about movie types. I'm not pronouncing this word because I can't. I tried, believe me. That's why I will be using types instead. And it's supposed to show you how does machine learning algorithm work. And I think it doesn't tell you that, and I'll point that out while I'm explaining it. That's why I took this example deliberately, to show you how machines don't think, or actually that machines are not thinking at all. It's just down deep math. Sometimes very complicated math, but just math, equations, numbers. The example is as follows. We have a list of movies. We have a title, and someone went through the effort, watched all those movies, and counted how many times people were kicked and how many times people kissed. Those are not real numbers. I actually didn't go through those movies and didn't count that. I just make those numbers up. But let's imagine someone did, and those numbers are real. And then, based also on the observation, someone attached the movie type as the separate column. So the machine learning task would be, based on those data, if a new example, new movie comes up, and you have the information about the kisses and kicks, assign the movie type. And when I saw this example, I was thinking, wait a minute. Well, I have a new movie, and I can assign the type just straight away, based on title, most of the times. If I watch the movie, I really didn't count those kisses and kicks. Even if someone provides me with this information, me as a human being, I don't use this information. But if you think of how machines are thinking, they see it like this. For them, it's numbers. For them, those titles are meaningless. They don't have any emotions. They are not actually watching movies. Even though nowadays, all those cognitive services, all those available API are trying to convince you that they do understand the written text and they can get the information about the movie by watching it, they get the numbers. They are not getting a feeling. They are not understand the movie. They are not actually watching the movie. They are gathering information. They're gathering numbers. So, in general, if you have a table of data and you have some rows, feature 1 and feature 2, you have a class A and B. Again, you as a human, not the machine. New example comes in. Feature 1 is 31, feature 2 is 4. Which class would you assign the new example to? Yeah? B. And how did you do it? So what made you decide that those features belong to class B? They're similar. So, as humans, we are constantly looking for patterns. If you try to make machine find the class, you need to tell them what they are looking for. Either you tell them, find me similar examples, and then you need to define what similar means, because the machine won't understand that. Or, when I got the answer, like, people only look at the feature 1, and only 2 examples of huge feature 1 were of the class B. So some people didn't even look at the feature 2. This is how you present the solution to the machine, but this is not how the machines are thinking, again. So what if you have let's say, not 5, but 5,000 examples, and yeah, let's say 5,000 examples. What would you do to figure out the new class? The class of the new example? Any ideas? Because it wouldn't be this easy, right, to look through the numbers for 5,000 examples and actually find the pattern, unless you are the natural pattern finder, which as people, sometimes we are, but I just gave you 5,000. What about 50 million? Any idea how to?
Find a line of best fit between the data points, and whichever side the new example fits on, you set that class.
That's the solution I will show you. Yes, that's a very good point. So we can find the line that separates one class of the other. To find the line, as humans, what would we do? Sorry? Yes, find some statistics, right? So the approach we usually do in data science is we try to visualize stuff. And it's, you can say like, those are the numbers that belong to the class A, those are the dots that belong to the class B, this is the line that I just heard. And we could say, well, everything on the left side of this line is of a class A, so whenever the new example comes in, for example, like here, it will be of the class A. Everything on the right will be of the class B. And this is, again, as humans. What if we have not 2 features, but 50 features, or 500 features? How would we visualize that? How would we find a hyperia to do it? It would be much harder, because me personally, again, I don't want to offend anyone, I only see in 3 dimensions. So visualizing more than 3 dimensions, it would be a challenge for me. Not to mention, I wouldn't really actually have the tools to present it to business people, for example. So visualization is great, but you can only take like 2, 3 variables, features at the time. But with machines, this is where they are great. They are not visualizing. They do visualization, but it's for us. But they don't think, oh, I cannot think in more than 3 dimensions, because they can. Machines take dimensions and just put calculations on that. So if you have tons of data, if you have a lot of dimensions, machines are bloody good in calculating stuff. The problem is, while we see the line is meaningless to machines. You need to say, this is the equation, this is how you calculate stuff, and from now on, use this equation and try to fit the coefficients of this equation, some parameters, but I'm basically telling my machine what's the solution. I just don't know the shape of this solution. This line can be very simple or it can be very complex. It can be like a rule system, but it's me telling the machine to find this particular shape of solution, and the machine is calculating the coefficients. Nothing really magical, although very often it's very, very complicated maths. This slide, I think, a little bit unfairly was in yesterday's pop quiz. I didn't realize it will be yesterday and my talk is today. I'm not breaking code of conduct. This is a very profitable job. If you search it online, you can get like 40K if you can do it. So what's the problem, and why am I talking about that? So I found an example to kind of show you that machine learning algorithms based on the historical data in some magical way are learning about the future, about the new examples. And this is the example of how human brain works. No one knows how human brain works, but we can see sometimes how does it apply to the, life, to the production. So, chick sexing. If you're producing eggs or meat, products from chickens, there is this problem. When they are small, no one knows about the gender. Or maybe put it differently, the gender matters in that case because the chicks are separated and have completely different fates, as you can imagine. So some are producing eggs, some are producing eggs in a different way, or are just killed and used for meat. The problem is, nobody knows what's the gender of the chick. That's actually not true. Some people do know, but they cannot explain it to you. They just, I don't know, if they look or feel, I don't want to know, but they have the capability of knowing the gender. The problem is this person that knows cannot explain it to the other person. But there are schools that teach you that. So how do they teach you if they cannot explain it to you? The student sits with the teacher. The students start to guess the gender of the chick, and the teacher is telling him, you're right, you're right, you're wrong, you're right, you're wrong. Based on that, apparently after a few weeks, the brain of the student rewires somehow, magically. And the student, after a few weeks, is capable of chick sexing. This is what we call supervised learning. So some old sources were calling it learning with the supervisor or learning with the teacher. And it's not actually true. The supervised part is that you have the right answer. You have the labels or you have the values of the historical data. So, for example, if we have, for example, classification problem, image with the cat and the dog. Let's say we have a system that its task is to classify if the picture is of the cat or of the dog. And we feed our system with those pictures, and we labeled them. So while learning, the machine, the computer, the algorithm knows, oh, this is a picture of the dog, this is a picture of the chick, of the cat. Like with chick sexing, there was a teacher and was putting the right labels. After a while, the algorithm is optimizing the coefficients, and based on those labels, it rewires, it calculates the parameters, and learns how to classify new examples. The problem is with overfitting, which is a glorified name for learning examples by heart. Very often this line is too exact, so you get very good accuracy on the training test and when a training set, and when you fill your algorithm with new examples, it totally crashes. It really does not perform well. So to prevent it, usually you do split of the training and testing set. Another branch of learning is unsupervised learning, and this is the one that is considered more cool, because you don't have the right answers, you don't have the labels. You're trying to find out something about the data, but it's very hard to actually evaluate your work, evaluate how your algorithm is performing, because no one knows the right answers. Usually the market validates your answer. So if you're applying it to clustering and you try to find the markets of people that are similar to you and you do it wrong, you just won't earn money. But it's not a very scientific method, right? So this is where people are really thinking, usually, when they think about machine learning. This is this finding patterns, finding rules, finding associations part of machine learning. So when I was doing my PhD, I had two problems. And one of them was that if we're doing machine learning, I was doing classification problems, so supervised learning. I had this nice workflow. So you got historical data with your labels. You need to prepare them because they usually are not, usable, basically. So you need to clean them. You need to think of which features are significant, which features you need to get rid of, which are redundant or correlated. So maybe you can get rid of some for the computation savings. And then once you have them, as I said, you're splitting the data on a training and testing data set. And then finally, you have this training set and the fun begins. But this part, especially the cleaning and data preparation, can take you up to 90% of your time. And then you have this 10% or 20% for the fun stuff, and then this is where you, as a data scientist, have fun, yada, 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 and then you have your trained model. It's performing very well. No, you don't know yet. How is it performing? First, you need to publish it somehow, you need to score it, and then you need to evaluate it. And for me, as a data scientist, all those other parts were kind of operational, DevOps, very boring. They're necessary because otherwise you don't know how your algorithm is performing. If you don't clean your data, you don't have any data to work on. But I was like missing some components or ready-to-use libraries which weren't available as easily back then as how it is now. And I was craving for the tool that could do those stuff for me or automate it somehow, so I don't write the code by myself. Because, you know, very often this code could be just wrong, and I could be just reassuring myself that I'm doing a good job. But the main reason was I wanted to do this fun part, and I wanted to push the boring work as far as possible. So this was one reason why I got frustrated when I was doing machine learning for the first time. So as I said, so a lot of those non-machine learning components in machine learning process that are necessary, but not that exciting. And another thing was, I built the model. I have something that is predicting if it's a cat or a dog, let's say. And I want to use it in my system, in my web app, in .NET app, for example, or, I don't know, Java, whatever, whichever you're writing your application at. And usually when you think of machine learning and people that are creating the model and people that are using the model, those are completely different teams. They very often don't speak the same language or don't want to speak the same language. They are both technology people, but they don't like to do it. So developers like to speak code, APIs, DevOps, and data scientists just like to do machine learning. They don't want to talk about infrastructure. In my opinion, they should talk better, but they are having constant fights. And an easy way to publish your model wasn't there. How people were doing it, let's imagine we have this line, we have those perfect coefficients, and we can distinguish between two classes. So data science people were serializing this model somewhere. Developers were picking up this model somewhere. And then there was this thing, well, okay, I have this line, but I'm not a data scientist. How do I use this line in my web application? And then you need to talk to those data science guys again, and it's all over again. So two things: automating not exciting tasks in machine learning and publishing it. And what I'm saying is, Azure ML is fixing it for me. And I will show you in a second in a demo how do I do it. But before I do that, I'm warning you, not that I will come and kill you if you don't listen to me, but there are so many articles, initiatives that are just telling you you need to be this tall to be a data scientist, that everything is out there just for you to reach. Everything is out there for you to reach, and you can use it. No one will forbid you, because almost everything is open source. The thing is, you really need to know your stuff to use it properly. You can use it somehow, it will produce some results, but if you don't know what you're doing, you will just reassure yourself that it's working well. I encourage you to write your own machine learning algorithm, but not to use your own machine learning algorithm implementation in productions, because there were people producing all those libraries, all those components for you to use, spending years on that, probably did it better than the project you would do during the weekend. Unless you're one of those people, then of course use your own algorithm. Then this doesn't apply. So everything I will show you, I hope, will look simple. It's not that easy if you don't have a background. So what is Azure Machine Learning Service? First of all, it's a drop and drag tool. So you have all those components. It will kind of resemble the machine learning workflow I just shown you. And second of all, once you have your model, once you train it, you just push a button and it publishes API. And the only thing your developers need to do now is just call your API with the new prediction, with the new data, and the API will just create a response with the prediction. And it's that simple. It's taking care of caching, it's taking care of authorization, authentication, and data science people don't even have to know about that. How does it work inside? So I'll show you some demo showing how machine learning works. It's a weird resolution, but let's hope it will work. So if you go to studio azureml.net, by the way, everything I'm showing you now is for free, so just go and use it. Oh, sign in. Sorry. So you can see I have, in a moment, I have quite a few experiments because I'm giving this talk for some time. If you want to create a new experiment, you just click New. And you can see that you have like a visualization of the last experiment I've created. Let's create a new experiment, blank experiment. If you don't want to use blank experiment, just want to see some samples, they are available here too. But I will show you everything from scratch. And right from the beginning, you get a tool that shows you like a canvas where to drag items. Unfortunately, this disappears after I drag the first item. Unfortunately and fortunately, because I know I used to be a software developer, how software developers hate drag and drop tools. But bear with me, it's an amazing tool. I was reluctant from the beginning, but then it solved so many of my problems. So remember this machine learning workflow I was showing you. First, I need to get my historical data. And this is a problem of its kind. So if you're in an organization, you usually have some data. If you want to learn machine learning, there are a lot of public data sets available, usually cleaned and ready for you to use. And the same thing is with Azure Machine Learning Studio. You have a lot of data sets available for you to just use. So you can see so many samples. Some of them are just taken from UCI, which is a very recognizable data set repository. What I will show you now, it will be a binary classification problem. So we'll try to predict the income. This is the data set, and let's have a look. How does it look like? Fortunately, the network is not the greatest, but should be fine. So you can already see that it has 32K rows, it has 15 columns, so it's not that easy to visualize all of them. And you can see the column names and even the preview of several rows. So we have stuff like age, education, occupation, relationship, race, gender, etc. And what we are trying to predict, the task is, we're trying to predict if the person that has all those features will gain income above or below 50K. So we have two labels. Either is above or either is below. And it's called binary classification because we only have two labels. So if you remember from the workflow, first thing we want to do once we have our data cleaned, and those data are quite clean because they prepared it for us, is to split your data test for the training and testing data set. you can look through all the components. There are so many of them, so you can see and try to search which one do you want. But I know the names, so I'll just put split data. And I'm just connecting the dots now. As you can see, the data set only has the output port, while every other component usually has at least two. At least one input and at least one output. In this case, we have two outputs. Why? Because we are splitting the data for the training and testing data set. So whatever comes on the left will be, well, if you say it would be like test data set, but you can revert the order, whatever you want. And on the right, there will be the rest of the data set. How do you do it? You just set up the fraction. So you can see, oh, I need to click. So you can see that there is a fraction. The industry standards is saying start from 0.8 for the data, for the training data set. So yeah, let's start with 0.8. So 80% of my data will train my algorithm. 20% I will use to test if it's performing well on the new examples. Once we have our data split, now we need to train our algorithm. And then I will use train model component. I'll make it a little bit smaller. So I'm connecting my trained model with my data, and it still has a problem. It has a problem because it doesn't know how to train it. I just told it, train it, but I didn't put the proper algorithm. I didn't say to my experiment, train it finding the line, train it finding a curve, or train it finding a decision tree. So it doesn't know which algorithm to use. And there are plenty of algorithms used for different kinds of problems. This is a classification problem, and I found an algorithm for you to show. It's called toClass. And then, if you can see, there are plenty of other algorithms you could use for toClass. Go to Azure Machine Learning Studio and play yourself. So I will use boosted decision tree, because it has nice visualization capabilities. So I'm saying, train this model based on this data and this algorithm, but it's still not happy. It's still not happy because machines are dumb. I shouldn't say that, because if they are actually becoming our overlords, they will remember. Anyway, they don't know what's my label. They don't know what I try to predict. This trained model is treating my income column like any other column with data, right? So I need to set up the task, find me the income. Now it's happy. So I could stop right there, but I wouldn't know if it's any good. So I could say, like, train me the model, I would find the model, and I'm happy, but I don't know if my data is any good, if my algorithm is any good, if I put a proper parameters on my boosted decision tree, because every algorithm has some hyperparameters. So what I want to do is, now I want to tell my algorithm, once it learned, well, now try to predict the income for the test data. We'll see how good you are. So it's called scoring, right? Score model. So I'm saying, score me this data. This time I'm using test data, using this trained model. And then I will have another column that will be, well, the income that my algorithm thinks it is after it was trained. And what do I do to find out if my algorithm is performing any good? Once I have real labels and predicted labels. Sorry?
Compare with the rest of 30% data.
Yeah, I'm actually, you're comparing the real labels and you're comparing the predicted labels, and you see how many times you're right. This is like the simplest thing you could do. sorry. In 29 minutes. You know, I have the solution for that. Yeah, we'll see. Come on, come on. See? I did it back then. Didn't work. Another one. Yeah. Just end task. Yes, worked. Okay. No, cancel. Anyway, we have our model scored, and now we want to evaluate our model. So I don't want to just do ifs and calculate how many times I was right, because there should be something that does it for me. There should be a component. And there is. Evaluate model. So I'm using evaluate model. This sizing thing is the least of my favorite, but it's the only thing I don't like. So now we have the whole experiment, and let's run it. So it's a very small, simple data set, quite a quick algorithm, so it will take like less than 10 seconds. But this is the most time-consuming part of machine learning. You're trying to learn your algorithm, depending on how much data you have, depending on how complicated data set you have, like how many dimensions, because then if you go deep down to some algorithms, they are based on matrices, and if you multiply them, etc., the computation cost could be huge. But very often you only have to do it once. Well, that's actually not true. If you try to tune your parameters, you're doing it over and over again. So you want to do it several times until you're sure. So let's see how good our algorithm is. Let's see how our trained model looks like. And remember, I chose the decision tree for the purpose of showing you that some algorithms have the form that you can actually explain to the human being once it decides to render. So it's a decision tree. If you know how does it work, it just takes the dimension and makes a decision go right or left based on some cut through the values. And if you have this in a final stage, you can easily translate it to even non-technical people, that this is the final decision tree, and this is how it works internally. Till very recent, decision trees weren't very accurate, but many companies were using them for this exact reason, because how they work was very transparent and understandable, and they were just sacrificing the accuracy because it was easier to have the buy-in from the business. So let's see how our model was scored, and if we visualize it, it will really resemble the dataset itself. Come on. Yay. So as you can remember, it had all those columns. It has less rows because we only take 20% of a testing set to actually score our model. And the data set just ended at the income, and we have 2 additional columns after scoring. And the way it works is, first there is this probability or a number from 0 to 1 assigned to your example. And if the number is less than 0.5, the classificator goes and say, this is the example of the class A. And if the number of probability is above 0.5, the classificator goes, this is a class B. The 0.5 is only a parameter. You can also set it up, like how the decision is made, because sometimes you need like 80 or 85% certainty. And even only then you can decide of a different class. So we can see how our labels were scored. So far so good. Some inconsistencies here and here. And then we should go through all of them, check if they match, and count how many times the new prediction was right. But as I told you, we don't have to because we have all the statistics about that here in evaluate model. So there are some pretty nice graphs and tons of numbers. And as you can see, accuracy is just one of them. And very often, it's very poor indication. Of course, if accuracy is very low, your algorithm is definitely not performing well. But it's just the beginning of what you should look at. Imagine a data set that is not uniformly distributed in terms of labels. Imagine cancer research. Only a few percentage of people actually have cancer. So if your classificator is just assigning the label that a person doesn't have cancer, it will have 90-something% of accuracy. It doesn't mean your classificator is any good if it's just assigning the label healthy to anything. So there are different indicators to show you if your classificator is any good. And remember I told you about the 0.5 threshold? You can change it here because you want to be more certain, or change it back depending, which label was A and which label was B. And all those numbers are changing, and you can see how those statistics are recalculated without you doing actual calculations. So this is very simple. This has 1, 2, 3, 4, 5, 6, 7 elements, and this is never how it looks like in real life, right? Let's have a look. 7, 6. I don't know how to count. That's why I need machines. It's very simple, and I hopefully shown you that in a simple way. But I knew what I was doing. I knew the tool. I knew stuff on machine learning. I knew which algorithm to choose. I knew all those components and what they are doing. And I've seen an error. I knew what it's expecting from me. Like any tool, it needs to be taught, or it requires learning. But it really, really isn't stuff. Especially when you're prototyping, when you're trying to find out, is this or this algorithm better for this specific problem? But, like with every ready-to-use components, you sometimes need to customize. And if you want to, customize, do stuff that are not there in the toolbox, what do we do in, development work? You write some code, right? You can do it here. It's not C# or Java. It's either R or Python. So either use R module. This was R model, but I'll try to find the one I'm looking for. Yeah, R script. The names also are changing, so I'm not really attached to them. And I'll try to, make it bigger. That's not the best idea you would have. It's just a placeholder. If you have your R script somewhere, develop it there, and then move it here, because this is not an IDE. This is a placeholder that you use your script, and it just shows you some ways how you could port other components that go through your code. So you use the ML map input port 1, 2, and you can also have an output. If you have your code, the same is with Python. If you have your code in some package, you can bring the whole package there and just use it inside there. So there is, I wouldn't say the easiest way of customizing your code, but it is very widely used. I was working with the clients that were using Azure ML only to write their R scripts there. And you would ask, why would anyone use this to launch their R scripts? There are probably a better way. So they did this for the second purpose I told you, that machine learning is sometimes hard, because they wanted an easy way to productionize their models. So let's go back to our model, and let's imagine we are data scientists and we want to give it to our developers so they can do the predictions. And how do we publish this model? There is an button here that we can set up the web service. I think I need to run it again first, because I was moving stuff around. It needs to run again, and we can set up the web service. So it says either I'm setting up predictive web service, or I'm setting up the web service that will retrain my model if my data changes. But let's set up the predicted web service. And what it does, it will do some magic now. Right? It's just moving stuff around. It looks pretty. So what it does, it adds two components. You can see there is web service input, web service output, and it removed some stuff and put something like this here. So this cube here is actually our experiment taken, the built model, serialized, and put here so that no one has to pick it up and know how to use it, because it's all done here. And it uses score model, because this is actually when something adds the label to the prediction. And it looks like it's using the data set, but it's not, because it's great, right? So it's not actually using the data set, it's using the schema of the data set. So it needs to know what are the input values, and then after scoring it, it just adds the additional two columns to the prediction. And the thing with machine learning is, it's sometimes very confusing. The separate thing is when you're training your model, and you have it, and another thing is using this model. So if we go back to this predicting income, if you're training the model, you're using every column, including income, because this is our label. When you're predicting the new values, you want to find out about the income. The income is not your input parameter. So this is not doing the whole job for you. If you want a very nice web service here, you would need to go and work on those columns, because you want to get rid of the income as an input parameter. I don't know if I'm explaining it correctly. For the output parameters, the default behavior is take everything that was on the input and add those two columns of the scored component, but maybe you just want the label, and that's it. You don't want to see the input values. Maybe you do. That's the choice. So you can tweak this, or you can see how does it look when it's just defaultly set up. So let's see how does it look. We first need to run it. Again, a few seconds. Yeah, so now we have web service running somewhere, and now we can deploy it. Well, actually, now we have built web service, and now we have to run it somewhere. This is a different tab, as you can see. We were here at experiments. Now we are at web services. And this is something that doesn't look very self-explanatory, but if you just go to request and response, you have the whole web page how to use it. So you just can just use curl or any REST client. You don't have to use Azure, .NET. Well, just curl it, and it will work. But you need to build a proper request. So you have the shape of the request here. You have information how will the response look like, what are the data types. And if you still don't want to do it, just go down, 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 and you have a code in C#, Python, and R on how to run this particular web service. In terms of authentication, you have an authentication key. So only people who know it will be able to run your web service. So you only give it to the people that are authorized, so basically your developers, or even not developers, to your CI server. So I don't think it can be made any easier. If you go back to web service, you can always check and see how does it look like. So as I told you, it took all of the schema, including the income at the moment, because I didn't tweak it. I just left it as it was on default. And I won't run it now because I don't know the actual values. But if you run it, it just calls this web API, and the answer just shows here. Oh, it did. Oh, there you go. Yeah, this was just about the experiment created. But if I test it now and don't put any values, some of the values are expected not to be null. Oh no, it actually returns something. So if you go to the details, yeah, you can see about the values, but not all of the values, I bet, because there are some missing one. But you probably could see it like in developers' tools. But it's not it's not the production way of doing it. It's just for you to check if your experiment, if your web service actually worked, was deployed, etc. If you're working with the business people, you might be interested in Excel stuff. It's like Excel sheet already pre-configured to use this web service. But as I told you, it's just the REST API call. So you can do it from anywhere, and anyone can do it. I think we have just a few minutes, so just tell you about my another demo, so just skip the slides. If you don't want to start from scratch, there are plenty of people collaborating. You go to Cortana Intelligence Suite, in Cortana Intelligence Gallery, and if you're looking for something, my example is Twitter sentiment, you can see other people creating solutions like this. Sometimes they are even publishing their web services. So you can copy their web service with already trained experiment and use it in your system, if you trust their data. Because if you think of Twitter sentiment analysis, this is something you can train on any Twitter feed, right? But it's rarely the case. Usually, for example, you're doing predictive maintenance, your machines, your devices will generate different data than some people doing predictive analysis on the Cortana gallery. So you need to train your algorithm with your data. But with Twitter, well, text is text, right? Unless you really want to feel the sentiment of some specific group, then you need your specific tweets, and then you need to go through them and label them, which is not a funny task. So if you do something like this, I want to see how does it work. You don't even have to go. This one is actually very, very well documented, but you know from your life that it's not rarely the case. If you just want to see how it's done, and see, free. It takes some time because it takes their experiment and copies it to my workspace. And there it is. Come on. There it is. I have my experiment in my workspace, and I can use it. This one is actually much more complicated. It has stuff like feature hashing, feature selection, because working with text only recently became a thing that we know how to approach. For years, it was a very, very hard task. The same is with images, natural language, etc. But if you start learning machine learning, it usually is based on numbers and labels, so very tabular data, not the text data. But as you can see, this is something that shows that Azure ML can also deal with text data. It has the capabilities, has the components. So the last thing I want to tell you, if I go to my slides, last thing is about the future of Azure ML. And I just checked this week, and it looks like it's not the future, it's the current state, because I was giving this talk a few times, and there are some videos flying around, and you see their studio and your studio if you go there, or the studio I've just shown. It looks completely different because it's constantly changing. There are new components added, some of them are deprecated, new features added. So you're creating your experiment and you want to troubleshoot and see some stuff. It improved massively. So now the error messages are much more meaningful and actually can point you to what you did wrong. But again, those are like syntax errors. So it's like you plumbed those components wrongly. It won't tell you that, well, you're trying to do regression and using classification algorithm. It won't tell you it's just wrong in terms of machine learning itself. And history and version control. So for the very recent few weeks back, like 2 weeks back, the only way of you seeing what did you do, or how did you change the experiment, was to look at the history, because there is like a log file that's showing what you did while creating and changing the experiment. Now you can, download your experiment in a JSON file and put it in any version control you want, and have it in your CI process, or just to collaborate with other people, or just to, control the version of your experiment. The same as with web service. It's also serialized, and you can put it in a JSON file. It's still not great, because you need to use some PowerShell scripts, but it's getting there because everyone is asking for that. And if you don't like drag and drop, if you're a coder, you can use Jupyter notebooks. So you can use R, you can use Python, and Scala, I think. I only use it for R and Python. So you write your code in using any library you want, scikit-learn, or I don't know, PySpark, some machine learning libraries, tons of them are out there. And then you just publish it as a web service. And this is what the client of R was doing. They were just putting their R code there and using publishing web service capability, because it was so easy for them to productionize what the data scientists were doing. It goes better. Imagine you're producing your R or Python code somewhere completely different, not in Azure ML, not in Azure ML Jupyter notebooks, somewhere else on your computer. And you want to publish this as a web service. There are packages for just publishing this. All you need to have a workspace, obviously, because this is how it's hosted. And then you say, publish this code in this workspace. Ta-da! You have your model built on your laptop, productionized. So to summarize, we talked a little bit about machine learning and chicksexing. I've shown you my 2 concerns about how machine learning can be more exciting. And then I've shown you the tool. And I encourage you to go learn, try it out, and collaborate in Cortana Intelligence Gallery. This is all. Thank you so much for joining me today. And if you have any questions, I'll be around